will start with a short introduction of the Virtual Vehicle Research Center. We are a research and competence center in the south of Austria, in Graz. We are the biggest research center for virtual development for automotive industry. We have started 2002 with a small center in the Austrian and German region. We have grown in the European market, also on the Horizon projects, on different Horizon projects, and contract research through our different K2 mobility funding possibilities. And in the end, now actually we are, let's say, a global player on the research side, especially for virtual development, on different aspects and different fields of activities, which you can see here. So we are working on, as I said before, mainly automotive and rail applications, but we are also working actually on energy, defense, some maritime, and also healthcare projects, where we are doing mainly the virtual development of different tools, methods, products, and so on. And what we will today have, our main focus is the materials and mechanical structures implementation, and also the road to user safety at virtual development and validation. So what is the Virtual Vehicle Research Center funded for? So we are a little bit a bridge between the scientific work at the universities and the industrial applications, where this output has to be used. We have our own funding scheme, that's Comet K2 program. We are working on different closed and also ongoing funded project on Horizon level. And we have also some contract works with different OEMs and tier ones in our partner network, so we can provide there also different services for our partners and customers. Our partner network, we have, let's say, nearly every main OEM in the European market and the American market. We have a lot of different tier ones, scientific partners for our different research projects, and also in the rail specific and health specific sector, we have some partners where we are working on different projects. The main point for today is a little bit material mechanical system. So that's a research field where I'm working on since 15 years, where we have different fields of activities like crash applications. We are actually working on different joining technologies and implementation in standard solvers for finite element simulations. Optimization and lightweight design is also a point which is main focus on FlexCrest project. And since a few years, we are working on this sustainable bio-based materials for sustainable applications in automotive and mobility sector. So that was a short introduction of the virtual vehicle and what you can expect from today's presentations. From the agenda, I will now hand over to my colleague Sergi from Eurecat, who will give you a short introduction of the FlexCrest project, and I will hand over after the presentation and give you a little bit more in-depth detail of the virtual testing of our adaptive and active solution.
Great, thank you, Christian, for the introduction. As mentioned, my name is Sergi Perreda. I'm the technical coordination of the coordinator of the FlexCrest project, and also I'm a researcher at Eurecat, which is a research institute in Spain. And I will give you just a short overview of the FlexCrest project. In this way, you will have an idea on what we are doing here. Here, just to have the main points. We'll see a little bit the project, the consortium, and then also the relevant points that we are working in the project. That, of course, as you can imagine by the name of the project, we are talking always a crisis situation. Here are some numbers about the project. It's a project of 48 months. We have a budget of about 4 million euros with 11 partners and from 6 different countries. So the main point here is that we can cover, that we are covering all the value chain of the development of knowledge and also the application of this knowledge in the real scenarios, right? So as you can see here about the consortium, we have research centers, as mentioned, at Eurecat, Fraunhofer, and virtual vehicle. So today, mostly all the contributions are from the virtual vehicle and also from our side, from Eurecat, that we are the coordinator of this project. Then we have different universities, Lund University in the north, Sweden, and then also CREMS, different or relevant industries in this automotive field. So GMA, Gestam, Aerobase, and also Idria. Some of them doing some simulations, and the other ones doing more the production, or more involved, let's say, in the production of these different components. And then, for sure, let's say, the final user of all of this technology that we are developing. Here we have Stellantis giving their requirements and also their insights for these developments. And of course, we have also here this standardization body, UNE, in order to develop new standards, to apply all of these different knowledge that we are developing in the project. So they are always just developing these new standards to be applied in this automotive field. Okay? So let's jump to the ambition of the project. As you can see over here with this animation, we are talking about the crash situation, crash scenarios. So our main ambition or our main aim in this project is that all of you know about the regulation of the CO2 emissions, etc., and the need for the reduction of these CO2 emissions. So reduce the weight of the vehicle is one of the best solutions. But if we are reducing the weight of the vehicle, what we want is to improve or at least maintain the same safety of the occupant, right? So the people inside of the vehicle. So this is our main aim, to try to have a lighter and also a safer vehicles in the future. So here I have just a short video. It's just 1 minute long, and I think that it can give us a good insight of the project. I hope that it works properly. Let's say you can, or maybe not, because I can hear it. Well, if not, here you have the link. We will just share this presentation with all of you afterwards, so you can just then click to the link and see the video. Okay, so because now I think that the audio is not working properly, so we can just jump to the next one. So then let's see the main motivation. As you can see over here, as we discussed, what we want is to design a lighter vehicle, but also a safer vehicle. In this case, we are focusing on the frontal part of the vehicle, since it's one of the most critical parts for the safety. And in this case, the new part is that you can see in the right-hand side is that we are including that what we want is a full aluminum design in order to reduce the weight of the vehicle, and then also to assess this full crash validation. That is all the information that you will see in the next presentation, right? So, but basically what we want is just to design a proper frontal structure to absorb and dissipate all of this energy during the crash. Okay, so to do that, what we have done, just very briefly, gather all the information, right? We are just following standards, the recap scenarios, and then gather information about the dash panel intrusion, the different decelerations that we have in the vehicle, in order to mitigate the damage to the occupants. And finally, of course, we need to know the kinematics and the chronology that we are having during this impact, right? This impact situation. To do that, we have just used the GLab model by Gestam, where we are having this reference situation or reference structure made of steel, and then we are moving to a full aluminum frontal structure. In this case, here you can see a little bit the path that we just followed. At the very beginning, we started with a HPDC aluminum part from a previous project, the Salema project, where they just developed this component just to prove the technology. And we tried to implement it into our GLab model, right? But since we are having new partners in the consortium, we have the manufacturer Idria. We just developed a totally new HPDC part and also new extruded profiles with new alloys in order just to have this better performance of these components. And then also you can see in the right hand side that there is something in the middle of this HPDC part. We will see later on, but it's more related on the active safety of the vehicle, right? And then here, all the processes that we just followed. We started, of course, knowing the situations that we have, the different load scenarios that we are having in our vehicle, but also in order to develop proper materials and proper solutions, we just develop new testing procedures about fracture toughness mostly, in order just to see which is the best aluminum alloy for these profiles that will the main components, the dissipating energy. Then, of course, the HPDC optimization, although that it is not a component or a material really suitable for these situations, we just wanted to prove that we can design it for crash situations. And here you can also see the AVFFs. So basically, we are using hybrid manufacturing. That this is another relevant point, or one of the relevant points of our project. That what we want is just to use additive manufacturing to reinforce locally the extruded profiles or the different components that we are having in our vehicle in order to have a proper crash performance while we are reducing the weight of the vehicle. So basically what we are doing in the extruded profiles, what we are doing is using this additive manufacturing LMD process to have the deposition or these rips on top of these extruded profiles in order to reinforce locally some parts, and then we can just use the unreinforced ones as a crash triggers. So by using these strategies, we can achieve a reduction of at least 12% of these components, and of course maintaining the same energy dissipation. So here you can see that we just developed quite a lot of different patterns, the fishbone, the honeycomb patterns, and also we just produced a lot of different combinations with longer gaps, shorter gaps, more ribs, less ribs, etc. So as you saw in the previous slide at the end is and we just followed an optimization process, as you can see here, we produce quite a lot of different different ribs, different structures, in order just to set up the process and see that everything is working properly. So this is when we are just talking about this AVFF in the project, that probably you will just hear a little bit about this. We are talking about this adding valid function of features. So at the end, these ribs that we are introducing in our components by using the laser method position. And to do that, we also develop new aluminum alloys by using zirconium, for instance, new powders for this additive manufacturing process in order to improve the performance of these ribs. So this is also a relevant point in our project. And here, then finally, we have the demonstration of the results. So we just we're manufacturing, in fact, the demonstrators of our project. So the idea is just to see what happens when we are also having non-standard crash situations, when we are just changing the speeds, the angles. Well, you will hear more in the next presentations. So how we can address that. And our proposal is to have new active systems in order just to accommodate these different crisis scenarios. So just to summarize a little bit, what we're having here in the project, what we are developing is this passive system that you can see in the left-hand side. So we're having the bumper, the extrude profiles, or the crash boxes, let's say, and then the HPDC part with this active system that at the end is a tank where we have a fluid inside, and we are just tuning how we are just removing, let's say, this fluid from this tank, and then we can just accommodate or tune a little bit the crash behavior of our vehicle, right? So then we have the as you can see over here, the HPDC part, the extruded parts, the laser melting deposition. So by coupling these different technologies, we have this hybrid manufacturing strategy. And of course, we are putting here this active system. That is the one that you can see in the right-hand side. So the full assembly, of course, we're having this kind of actuator or with this tank that we are just developed, especially for this situations in our vehicle, in our crisis scenario. So just to conclude, then just some takeaways that I just wanted that you have in mind for the project. So basically what we are doing is developing new structures for crash situations, in order to reduce the weight of the vehicle, but maintaining the same crash performance. Then by using the aluminum alloys and also similar aluminum alloys, then what we want is just improve the recyclability of the vehicle. And of course, this also has an impact on the environment. Then having this different or this hybrid technology to manufacture these components. So we are proving and we are showing that we can use quite a lot of different technologies in order to manufacture these crash structures, from extrude profiles, additive manufacturing, and also HPDC, high pressure die casting process in order just to produce these components. And finally, all the relevant part about simulation and how we can predict the different crash situations, how we can just adapt our structure in order to design the vehicle, but also how we can just use these simulations to for this virtual homologation of our vehicles that we will design in the future. So with this, I can just close my presentation, and now I give the floor to Christian once again.
So thank you very much, Sergi, for the insights on the whole project FlexCrash. I have to skip a few slides, I think, because they're double from your presentation.
Okay.
I hope everything else is then new for our participants. So let's now you hopefully can see.
Yes.
Our presentation, especially on the virtual development and virtual testing of these, from Sergi mentioned, active and adaptive crash tolerance structures. So first slide, FlexCrash general overview. I will skip about the FlexCrash project also. So what's the research beyond the state of the art? As Sergi mentioned before, the main goal is to lightweight the vehicle as much as possible, because less weight means less fuel or energy consumption during operation, and we have a very efficient mobility solution. On the other side, we want to have, or we want to increase the passenger safety. The main problem with these two targets, they do not fit together. So when you are lightweighting the vehicle, passenger safety decreases typically. So how can we tackle that problem? Is the main research question on the FlexCrash project. So how can we make the vehicle on the one hand side more lightweight, and on the other hand also increase the passenger safety by adapting classic solutions with adaptable manufacturing technologies and an active system that will help the passive structure to increase passenger safety on different crash loading scenarios for the future mixed traffic possibilities. So for 5 different pillars where our solution is working on. So we, as virtual vehicle, with the partners from the Technical University of Luleå and Aerobase and also Gestamp, are working on the crash simulation from the advanced material simulation up to the virtual testing in the full vehicle. So that's one pillar. The second pillar is the manufacturing side. So that has to be flexible and also hybrid with different manufacturing technologies to assure that our solutions is on the one hand side manufacturable able and also provide the developed safety for the passenger. The third pillar is then the structure itself. So we have to optimize our patterns, our structures, and active system on the different loading scenarios that we have also worked on at the beginning of the project. Then the advanced testing from the material itself up to component level and sub-component level in the, or sub full vehicle level in the end, that we will have to be carried out in the end of the project in the next half to 1 year, just to validate our virtual work and our virtual testing that we are actually working on. And in the end, the different safety needs for especially future mobility when it comes to mixed traffic scenarios or the crash scenarios, which will differ from actual crash scenarios because of different ADAS systems, self-driving vehicles, and so on. So these has to be also think of how we can implement that for future regulatives and Euro NCAP, for example, that has to be tested on new generation of vehicles. So what are the future relevant crash scenarios we found, and we are then set up our work on. We have this crash reconstruction pipeline from the IMC Krems, which is one of our project partners, where we can simulate different scenarios. We can generate different ADAS opportunities that we have. We can simulate driver behavior, and from this driving agent behavior, we can jump to our passive safety simulation and development. We have the opportunity here to change different scenarios. We can use this pipeline for also scenario creation for future mixed traffic, and we can use these data for our optimization on different angles, velocities, and so on. So from our research and our scenario generator, we have found 3 different crash scenarios, which will be the main scenarios within the future mixed traffic. And from these 3 different scenarios, we have these configurations for our testing of our system. So we have these 3 different front crash scenarios, and we choose for the main validation and virtual testing the bottom right one, because that's the most severe one for passenger safety. From these crash scenarios, as Sergio mentioned before, we are able to use the Gestam GLab virtual model as a demonstrator, where we have started with the standard steel front end. We have modified these front end system with a full aluminium crash structure, as you can see at the right top picture. And I have an old version from the Salema or from the HPDC part. So that's a combination of an aluminium extruded part in the front rail, which will be modified with different additive manufacturing and welding patterns. And in the rear end, the HPDC part, which is in the last version highly modified by Hydria and our optimization. And there is integrated these mentioned before active solution for adaptability of the full front end crash behavior. What was necessary for that? So as Sergio also mentioned before, was material development, so that we can use these different recycled aluminium alloys for these welding process to adapt a quite simple base structure. So that the goal was to have an extruded, simple designed front rail, which will be strengthened with different patterns and just modified for the different loading scenarios, weight of the vehicle, and so on, so that we can adapt these simple extruded profile with whatever pattern, with whatever structure we need to adapt the crash performance of the front rail system. So in the end, when we go to virtual development, virtual testing, we have in the upper left animation the standard front rail without any patterns on it, and in the bottom left animation the simplified patterns on the structure. And what you can see here is the energy consumption between these different solutions. So we are gaining about 30% energy consumption with the same base line extruded profile. Just to we just implement there these different welding patterns to adapt the crash performance of the front rail. So that's one of the technical solutions for the adaptability of quite simple produced parts. So with different pattern optimization directly on the extruded profile. The second solution, that's the new version, is the right-hand side, the high pressure die casting part. Now nearly the last version from Hydria, which is optimized with our support for the crash pulse and the performance. And the main goal was to have an robust and predictable one hand side material card, and also a methodology how to implement such structures in a full vehicle simulation, because this active system is not so easy to handle in a finite element simulation. And just to give you an impression how these could work, so we compress the front rail, and when the front rail is fully compressed, then the active system starts to work and modify the front end crash behavior dependent on the different loading scenarios and also on the different crash partners, velocity and weight, for example, that can be used from vehicle-to-vehicle communication, for example. And we can adapt that directly the active system and increase the compatibility between different crash partners. When we are going to, let's say, virtual development, just to give you a little bit of feeling how robust or not so robust these simulations could be. There is just one change in a little rib in the HPDC part, and you can see here a different behavior from the front rail system, and you can imagine if you have there a little bit not so validated or not fully validated material cards, then this can occur in your simulation, and this affects your total development process. And for that, the virtual testing and virtual validation of material cards and methods is so crucial for the development of such safety relevant structures. Why are we doing that? Actually, on the left bottom side, you can see a picture of different loading scenarios from Eurecat that has to be tested for the vehicle manufacturer. That's a lot of different testing scenarios, but in future, that these test metrics becomes even more bigger and bigger, because real scenarios should be implemented in these regulatives, and for that you can only test and validate your system, your crash structure virtually. That doesn't work in real world testing. So the virtual testing and virtual prediction of the behavior of the different structures will get more and more important. And for that, you need really good validated material cards and methods how to predict your behavior to enhance, in the end, the vehicle safety, as said before, because of these two different targets that we have. On the one hand side, the lighter vehicles, and on the other hand, the higher passenger safety, to increase passenger safety. And the pipeline, let's say, from FlexCrash is a combination of a passive structure and the active system that we are implementing in the front end crash structure to in the end have an optimal deceleration pulse for the passengers in the different vehicles. And not directly virtual development, but manufacturing technologies also have to be mentioned here, because that's the crucial point, that these manufacturing technologies go hand in hand with the virtual development, because we need to know if the different technologies are working, are fit together, and that's also a main point of the FlexCrash project, to ensure that these technologies are working especially for crash applications. And in the end, when it comes to recycled aluminium, the environmental sustainability is also a big point for EU goals of reducing greenhouse gas emissions up to 2030. So that was a quick overview of the virtual testing, virtual validation part of the FlexCrash project. If there are any questions, please, we have this Q&A session in the end of the webinar. And thank you very much for a time, and I will hand over to my colleague Stefan Kirschbichler, who will present the Ad Safety project I mentioned before. That's a national funded project coordinated by the Technical University of Graz. And I will start the presentation in 1 second. I see the overview of Ad Safety. I will hand over to Stefan.
Hello, everyone. Welcome to this webinar. And yes, as Christian mentioned, I have the honor to present you a big funded project to the topic of virtual testing. One moment. Just one moment to share the right slides. Okay, so sorry for this interruption. The project, it's called Advanced, or the short name is Ad Safety. It's Advanced Efficient Development of Robust Vehicle Safety. So it's more in the area of active safety, of course. And the coordinator of the project is University of Vehicle Safety, also located next to our office. So what's the project about? Technical issues. So, but everyone can see the slide now.
Yes.
Okay, perfect. So I want to tell you about the Ad Safety project. So what's the...
Can you put it in presentation mode?
No, that doesn't work. That's the problem.
Okay.
That's the problem. But I hope it's for everyone possible to see the information on the slides. So what's the problem? Also, Christian talked before, vehicle safety is still a lot of tested efforts and also mostly developed in very simplified lab conditions with limited real-world safety inputs, which occur. And maybe most of you also know where the Euro NCAP requires more robustness of safety systems and also introduces for that reason several virtual testing load cases as well for active and passive safety evaluations in 2026. So at the moment they started also with the evaluation of an HPM model in vehicle, and there will be, of course, further increasement in the upcoming years. So for us and also for a lot of industry partner, of course, the virtual testing is promising to achieve more robust safety evaluation and also maybe new possibilities and also new test cases. But for this situation, we need really predictive simulation methods and a robust safety system design. That's at the moment a little bit limited because the trust in different simulations types and also how you can qualify simulation of models for this, for example, Euro NCAP testing, and therefore you, of course, at the moment you need a lot of validation tests too. So what's the big question is how to develop robust safety systems which are based on your predictive simulation methods and with not increasing the number of required hardware tests in a useful way. So the current situation we talked about, we have limited real-world safety addressed in some test cases. At the moment, what we are working with a lot of industry partner at the moment, where they try to increase the virtual testing in their houses. They also have to increase the hardware tests at the moment to do the validation part, and that also increases the costs a lot, and that's not very very useful. And so the Ed Safety ambition. So Ed Safety is a national funded project with about 6 million euros for a time period of 4 years. We are at the moment in the first project phase, and I will also show you the partnership in the end. But what's the main part? It's to improve this kind of hybrid testing. So to really just to conduct the necessary hardware tests and also component tests in a parallel way to see how we can make the simulations more benefit and boundary conditions. That's one main task. So to reduce also the development costs and also to be possible in the end to have maybe also use cases in the simulation which are maybe too difficult or too dangerous for hardware testing. So the idea behind it's, of course, the most main part is the more robust vehicle safety systems with, of course, not only benefits or test cases from per law or Euro NCAP, for example, but also from real world benefits. So we need more robust evaluation scenarios, which will be defined in the project. We also need a way for qualification for passive and active safety simulation models, which are allowed. So, for example, for the Euro NCAP HPM test cases in Euro NCAP, you have to qualify your used simulation HPM. There are some validation cases you have to simulate before, and when you have the qualification from Euro NCAP, you are allowed to use it in the simulation. Therefore, we need maybe also new methods for selecting these test cases and simulations. And of course, we need more methods to prepare or to agree on simulation software models from different companies, for example, as also for the slot courses. And we need, of course, a quantification of these benefits for these safety systems. Therefore, the project is one big project with 4 work package. We have methods for active safety simulation, model calibration, validation. That's for the active part, so where we are mainly involved. We have similar for methods for passive safety. There are some use cases with occupants, and nevertheless, we have here improvement with hardware testing tools on test tracks for the calibration, of course, of simulation models. And we have in the end quantification to see how the benefits and how the measurement parameters and so influence all the simulation models in the end. What's our part in this project? We are more on the active side. So our part is we have in our house, or our motivation is, of course, we have all these topics about road user safety. We have the boundary conditions and requirements like Euro NCAP, NHTSA, also C NCAP. We have in our company autonomous vehicle. It's our Ford Fusion. So it was the first vehicle which was allowed on test tracks, of course, and also some streets to drive autonomous, of course, with test driver. And we are going to do the virtual validation and develop a digital twin for acceptance, for example, with declarative, so that we have in the end a method or process which will allow the customer, or in this case, the project's partner, to have a whole virtual test setup, for example, in this case for Euro NCAP. So what's here the main part, of course, for this digital twin? At the moment, we are at the status that we have already our test vehicle, already a simulation tool in the CarMaker, EPG CarMaker software. now we are in the process to do the validation and verification. We have, of course, that we are also partner of Eurecat. So Austria is partner in Eurecat since 2022. Virtual Vehicle is here, partner with Safety Labs Austria, and we are addressing the virtual active part. So we are here working in the working group for setting up all these methods and roadmaps for Eurecat together with the other Eurecat partners. It's at the moment, so we have here our proving ground in Austria, where we have already a full digital map of this testing area. At the moment, we are working together with our partners and to verify and to do process for the validation of the targets for the tests. And of course, we have our vehicle test, this is our Ford Fusion, which is from software side for our company completely open. So we have possibility to read out, of course, the test data and also have the information on the measurement system, sensors, cameras, and all, and that we are at the moment going to implement in the software. So what's the approach for this digital twin setup? Of course, you have first to define and implement a process for all these models and the way and the method to have here all the data in the software you need. This includes also the process for the surroundings module. We have also to have the whole information from the vehicle, what depending on vehicle dynamics and so on. We have here also to include and to find a method for the sensors. So first of all, in this phase for our vehicle, so because it's open and we have the information, but it should be defined a method also for other industry partners or process how to do or to integrate this sensor information in different softwares, not only CAMEC, also in other possibilities. That's the status at the moment. So just some info about the proving ground. It's Euro NCAP accepted proving ground, 2 hours away from Graz, where we work together, of course. We also have here the whole information of surface and slopes, gradients, everything is available and also needed for the support systems and also testing the Euro NCAP requirements. We have partners like Alplab, which support us with hardware equipment, and we are currently working on the validation for the software at the moment. And of course, our vehicle, so as mentioned, it's a Ford Fusion, which is equipped with different sensor types, cameras, everything is necessary. We have this, I would say, this demonstrator, this vehicle already for 8-9 years, and have quite a lot of different, tried a lot of different measurement equipment and systems, and all this know-how and these methods we are learning for the last years are now implemented in this process. Is of course a lot of work to do, but it's we are on a good way for that topic. If you are interested here for other projects, our vehicle is completely open for in projects for different possibilities. So depending in this case, we are using together in this project EPG car maker. So we have an exchange of hardware data from the vehicle to the simulation. We have also combining at the moment so sensor information which is measured directly by the vehicle, which will occur directly in the simulation model. And in the end, there should be, of course, the real test on test track, then the digital twin of the whole setup, so you are able to test different scenarios, measurement equipment, sensors, and should be in the end a method which could be used for Eurecat and also for other industries partners. And my last slide to this project, if you are interested. So as mentioned, the coordinator is University of Graz. We are here as Virtual Vehicle the scientific partners for the active part, of course, the testing partners. So AlpLab is responsible for the active safety testing. DSD is the company which owns the test track. Then we have also TechCon, so they are accredited for Eurecat passive testing. They are also located in Graz. And from the industry partners, we are here cooperating with VR Humanetics on the test equipment, software side, Andata, Carmaker, and AVL. So to make this happen for also active and passive. Then we have component supplier in the project, of course, for sensor systems, sensor types, and we also have here involved two German OEMs to have the method implemented and also have test vehicles and so on. So thank you for listening to this project overview, and sorry for the interruption, beginning with the software problem on laptop type. And yeah, thank you.
Thank you very much, Stefan, for that insight of the safety project. Apologize for the technical issues at the beginning. I hope we can solve that by presenting directly from the next presenter, Peter Wimmer, who will give an insight on the safety toolchain, which was developed at Virtual Vehicle together with different partners, and they're also part of the safety project. So I will hand over to Peter.
Excellent. It seems to work. So I have the pleasure of presenting to you the Virtual Vehicle Safety Toolchain, our method to perform effectiveness assessment of integrated vehicle safety systems by virtual simulation and testing. Let me briefly give you an overview what the Virtual Vehicle Safety Toolchain is. It is not a complete tool. It is even more. It is a collection of tools for virtual testing and prospective effectiveness assessment of various safety system types, so active, passive, and integrated vehicle safety. The main elements are as follows. We start with scenario generation, so we need to define a baseline which represents the situation that we have before we introduce, even virtually, a certain safety system. Then we directly start with our simulations, which are divided in several parts. The first one is dealing with the pre-crash phase. So there we have a scenario-based approach, which consists of all relevant components like vehicle, the driver, the safety system consisting of sensors, algorithm, actuators, and also the vehicle surrounding. If this simulation ends up in a crash, and this is for now, just as an example, the VRU setup, we have one or two stage in-crash simulation, which consists of various tools, which allow us then to determine the injury that is relevant for the final step. Of course, we have to do this not only once, but as we want to determine effectiveness, we have to do this many, many times. So this is also a challenge that I will also address later on. And the final step is then effectiveness assessment. So determine which kind of safety or how large the safety benefit is that we can obtain with a certain safety system or a safety system configuration. Regarding the baseline scenario generation, let me start with this very general slide. This is the image is taken from an ISO technical specification that I was also involved in developing. There we define several types of baseline approaches. Basically, we have three main approaches. The first one is just replicating real-world cases. This is what we call approach A. Approach B would then be extending these real-world cases with some distributions and modifying them and also increasing by thus the number of baseline cases. And approach C is a little bit different. It is not directly replicating or based on individual real-world cases, but it's based on distributions of parameters, relevant parameters taken from real world, but then generating synthetic cases based on these distributions. I would like to show you one approach that can be attributed to this synthetic case generation. This is something that we have developed. It's what we call scenario generator. It is based on crash data, as mentioned before already. It is capable of generate an arbitrary number of cases which are statistically representative, also include rare combinations, and it is built to produce scenarios for car-to-car and car-to-VRU test cases. This is a short overview. It has a GUI, obviously, where you can make some selections. What you will get as an output is information for a test case on the initial positions and speed profiles, so basically the trajectories of the involved participants in the simulation, but also environment conditions like dry wet or lighting conditions, so day night, which might be relevant for sensors and also for human drivers, and also for the VRU cases, some properties of the vulnerable road users like sex, age, height, weight, also with statistical data behind. Coming to the next main element, this is the continuous virtual simulation, and first of all the pre-crash part. Also here I would like to reference to the ISO technical specification. There is depicted a generic simulation framework for prospective safety performance assessment of pre-crash technology, and we stick quite closely to that. Maybe I go briefly through it. So we have four main elements, I would say. We have simulation control, which is more or less the conductor of the simulation. Then we have the vehicle surrounding, which is, well, there is everything in that is relevant around our vehicle under test. So this is traffic, so everything that moves. Infrastructure is everything that is static, like roads, buildings, and so on. And environment is, well, these are things that might change over time but do not move, like lighting conditions, weather, and so on. Then we have a synthetic block called sensor perception input generation. This block basically takes the information of the vehicle surrounding and transforms it so that it is appropriate for a sensor and also for the perception, because this needs to be somehow transformed, this information, to also reflect or that it is suitable for the capabilities of these sensing perception elements, which brings me already to the vehicle under test, which consists of course, the technology. This is typically the thing that we would like to assess. So this consists of sensor logic and actuator. I think this is quite logic or traditional, and the same for a driver, so perception, control, action. Both these elements are capable of controlling the vehicle. This is the vehicle dynamics part, so they can control, steer, and by thus influence the vehicle motion. And the final block is then the collision model, which of course consists of a collision detection, so that we know if a collision occurs. And if a collision occurs, we have the collision consequences model, which seems rather small here, but this can be also a lot and very complex. Okay, let's see how we did this. So you might recognize several components that you have seen in the previous slide. What we do here at Virtual Vehicle and in the safety toolchain is we take all these components and connect them via our virtual ADAS ADF integration platform, which is a co-simulation based approach. This approach allows us to, well, connect all the elements and also ensure that they communicate with each other in appropriate timing, and also that the scheduling, so that the models run when they are required. We can stop and they can start, because we have in crash. We don't need to start them in the pre-crash phase, and the other way around. This is one example of an exemplary setup for a VRU use case. So you can see that we can couple a lot of different simulation tools together to build an overall simulation that covers all the relevant aspects. Here the same, and this is more relevant also to the example that I'm going to show later. This is a setup for a car-to-car simulation or safety impact assessment. So also here you can see we have a lot of different types of simulations that we can connect. And the final element of the theoretical part and of the safety toolchain is then the injury risk-based effectiveness assessment. The simulation output are injury criteria values. I think this is quite obvious. What we then do next is transform the injury criteria using injury risk curves to an injury risk. And as we have a lot of simulation runs, we also have a lot of results. So this means we have to do some statistics to get finally results for each body region and the total result. Okay, sorry, I was just, yeah. So we get a region, a result for each body region and the total result in terms of numbers, but also graphical output. And the final step is then the actual effectiveness assessment, which means we compare the outcome of the treatment simulations, so the simulations with a safety system on board compared to the situation before, so the baseline. And then we get something like this. This is an exemplary result. I guess everybody can hear me? Yeah, I hope so. So we get numbers for various variations of a certain safety system or types of safety systems in numbers, but also as for here as an example as a box whisker plot. And this serves as a basis to decide then which safety system should be implemented. So summing up the theoretical part, what are the benefits of this virtual vehicle safety toolchain regarding the simulation? It's automatic, a continuous simulation for an arbitrary number of cases without any interaction. So this runs fully automatic. It is sensitive to a specific vehicle geometry and safety system configuration. And it can be easily adapted in terms of modeling detail or other models because it's a modular approach through this co-simulation. So we can very easily exchange a model because the interface is the same. So we can connect various types of models to quickly change the modeling detail of a certain element. Regarding the effectiveness assessment, we do a combined effectiveness assessment of active, passive, and integrated safety systems. The approach allows for a direct comparison of the different types of safety systems, and it is purely virtual, so we can use this in very early product development phases. Good. I will show you an example of an application of this. This has been done in cooperation with ZF. It is an example of a frontal collision scenarios with AEB and an advanced occupant protection system. We had this research question that we wanted to address. So this is as follows. What is the safety performance of a combination of an adaptable standard restraint system with a 50% male driver? So this is our passive safety system, and an AEB system, active system, in a variation of vehicle-to frontal crash configurations under consideration of human movements within the pre-crash phase. So we also, because the AEB decelerates and thus the occupants move in a way, and we wanted to consider also this movement or see which impact this has on the performance of the passive safety system. And the criteria that we used were impact speed and mainly AIS2 injury risk reduction. Briefly, the safety systems under test. The A-base system was configured as follows. It is TTC based, and we had two variants. Once it fired at TTC 0.6 seconds, and the other variation was 0.9 second firing time. And the action when firing was just hitting the brakes as hard as possible. For the restraint system, we had 4 parameters that were varied. So we have the airbag time to fire, the airbag vent hole diameter, belt retractor time to fire, and also the belt retractor load limiter level. This is hopefully familiar already to you. So we have these various components. We first built initial framework with high fidelity models. This looks as follows. We have, again, a scenario-based pre-crash simulation, so vehicle driver, active safety system surrounding. We have then a detailed vehicle in-crash simulation based on finite element models to determine the crash path. And in parallel to that, a continuous vehicle interior and occupant simulation for pre and in-crash phase. So as I mentioned before, we wanted, also the pre-crash motion. So this model is fed with the accelerations from the pre-crash phase, but also from the in-crash phase. And this model also delivers the output that we need for the determination of the injury severity. However, these two models, so the vehicle in-crash simulation and also the interior and occupant simulation, are rather slow, which is not ideal, I would say, if you want to calculate many cases. So we had to do something about this. So we slightly changed the configuration for the, I would say, full-blown safety performance. We have this setup. We have an interior, or the changes are mainly here. So the interior occupant pre-crash surrogate model, which is a simplified multi-body system model, which is much faster than the original one, the high fidelity one. And we have a combined model for the interior occupant and the in-crash surrogate model. So this combines crash estimation and also the motion and the passive safety system of the occupant in the in-crash phase. And these both are much faster and allow us to do these large scale calculations that we need for safety performance. Let me show you some results. We did baseline runs, which ended up with a mean impact speed of roughly 60 kilometers per hour. And we have an average AS2 plus risk of 0.7, so 70%. This risk is based on HIC and also chest deflection. This video shows an overview of the simulations. So the blue dots are the opponent vehicles, which all more or less, or sooner or later, end up in a collision, in a frontal collision with our vehicle, which is at the center point of this plot. Additionally, we did these variations of the AEB system. So we get a reduction, of course, hopefully, regarding impact speed, but also regarding injury risk. This time is rather late for firing, so we also had a one with earlier firing, and there we can see that the numbers reduce, so the impact speed goes down and also the injury risk. And finally, we did, and this is I said we also get distribution, so you can also see that the distributions move towards lower injury risk, going from baseline to TTC 0.6 to TTC 0.9. So we can very nicely quantify what kind of impact or what impact this introduction of these systems has. And regarding the passive safety systems, as our surrogate models are that fast, we did something that is, I think, really interesting. We did a restraint optimization. So we did, for each of the cases, we optimized the restraint system parameters to get the minimal injury risk for each cases individually. And this brings us, well, of course, here it doesn't change anything because it's still the same A/B system. But here you can see that we even further can reduce the injury severity. Yeah, I'll come to the final slides and the conclusions regarding the framework that we used specifically in this application. It covers the whole course of events from normal driving up to crash. It can consider the influence of active and passive safety system on injury risk, and it is capable of being used in a scenario-based assessment to cover a large range of scenarios and application areas for the safety systems. Regarding the surrogate models, they have a high potential to reduce simulation time while still being good in predicting the high fidelity model results. However, they need a training phase, but even including this, the overall process is faster than using the high fidelity models for all the scenarios. But of course, you have to put your brain power into how to set up the training process, and also regarding sampling strategy, which kind of modeling approach, and so on. Yeah, and in this study, we limited the range of application, but extension is, of course, possible to get further in this field. And that's all from my side. Thank you for listening. If you have any questions, try to put them in the chat, and I will try to answer them.
Thank you very much, Peter, for the insights of the projects for the virtual vehicle safety toolchain. And now I will hand over to Werner Leitgeb. He will give us some insights of the actual ongoing Horizon Europe project Protect Us, and also the closed project OSCAR, which sets up a little bit the baseline for all the work that we are doing in flex crash and at safety. So please, Werner, it's your turn.
Give me a second. Does it work?
No,
okay.
It works.
Then, hello everyone. My name is Werner Leitgeb. Looking at the participant list, some of you I know quite well. Nice to see you. I'm having the honor today of presenting a little bit on road user safety. This is very much linked to what you were hearing before, but it's kind of the last step in the procedure. Today I will tell you about road user safety. This is occupants and traditional vulnerable road users, active road users, as some of them tend to call them lately. A little bit of a background and context, also to see this in context with Flex Crash project. Tools and methods we are currently using, assessing road user safety, countermeasures impact, and I would like to plug in a little bit of an outlook, further work, and upcoming topics in the very end here. So in order to come to background and story, we are all doing this for one very big reason, and this is to protect road users from harm and injury. The EU has its current safety policy out there, which is called Vision Zero, and priorities there are, as we all can think of, infrastructure, safe road use, safe vehicles, post-impact care, and driving licenses. And in our a little bit closer context, this is about injury prevention and mitigation linked to vehicle safety. This is always the basis structural safety. This is what FlexCrash is doing. And this structural safety is kind of the absolute necessity to provide safety to the occupants themselves. Imagine vehicles from 40, 50, 60 years ago that simply did not have any crumple zone. That crumpled, then you can put safety belts and airbags in there as many as you want. It will still not survive. This is coupled with active safety that Peter and Stefan were talking about before. And this road user safety, of course, also our vulnerable road user safety. Coming again from vehicle side and infrastructure side, and a lot about user awareness. Last point here is human factors. So we're talking about people, people's doing and wrongdoing, and if everything fails, we have the topic of injury treatment, post-crash, hospitalization, therapies, rehabilitation, all these kind of things. So this is kind of the context here. And I am going to talk about today occupant safety topics, vulnerable road user safety topics on the vehicle side, and a little bit going into hospitalization, treatment, and these kind of topics. So I hope you understand the context now. And yeah, I will divide my presentation in two projects that I'm both happy and was happy to coordinate both of them. Oscar project from a couple of years back, kind of building some of the bases that are currently used in FlexCrash, and then we'll focus more on the current running project Protect Us that deals with long-term consequences. So back to Oscar. This is a project from Horizon 2020 program, so rather old, but still relevant. A lot of stuff evolved there. Premises back then were that future accident scenarios involving passenger cars need to be understood a lot better, especially in context of highly automated vehicles. Some people always think that vehicle automatization will remove accidents, will remove crashes, but I think we are all aware that this is maybe a very, very far distant future. Accidents will occur and will be a problem for the foreseeing future, especially in mixed traffic scenarios. In Oscar, we came to the point that especially critical crossing scenarios are difficult to control for highly automated vehicles, and coupling that with sitting positions that do not require the driver to sit straight behind the steering wheel might be a challenge for protection. So that was the basis and premises of Oscar project. In this context, we developed and further improved assessment methods, virtual assessment methods, and currently most of this assessment is done with crash test dummies. You all know them. This is the ones that we need for homologation, and this is the basis, for example, consumer testing like Eurecat or US NCAP or China NCAP. But Oscar back then foresaw, or many people in Oscar foresaw, that human body models will supplement these crash test dummies. And yeah, this project was very much about improving them, improving their omnidirectional biofidelity, activation of human body models for also enabling them to be used in pre-crash scenarios, these kind of things. And we got that far that currently EuroNCAP is using human body models already in the pre-assessment phase. So they're currently evaluating this, monitoring, so it's called monitoring phase there, and planning to use them finally from 2029 on in their protocols. So Oscar did a lot of pre-work and enabling this, and yeah, we all agree that these scenarios might need a democratization of models, looking a little bit into the more diverse population. And yeah, This is what we did then. A follow-up on that is the currently running Protectors project, where we look in a lot more detail in the injuries. What we want to do is protecting road users, all road user groups, from serious injury and long-term physical, cognitive, and mental health consequences. This is the critical part there, and we are doing that by interlinking research action between the traditional engineering methods that most of you in this webinar, myself and my colleagues and my former background was mostly focusing on, with medical needs and medical methods. So we are linking those groups with different terminology, different challenges, and yeah, very challenging and interesting mix of fields here. I will spare you most of the consortium, but you can see this is a mix between medical and engineering, traditionally engineering groups, from OEMs to research institutes, hospitals, and also European public health bodies in here in this project. And we are currently a little bit beyond halftime of the project, so still run for another year. What we want to do here is improving medical tools and epidemiological indicators in order to classify long-term consequences of injury. This is mostly done with our statisticians and medical hospitals, medical data. So this is ICUs, intensive care units, long-term terminology parts, and psychologists directly at the hospital, directly with patient data, and coupling this with our engineering background, our engineering tools, improving human body model assessment capability specifically for these long-term consequences. We all know that for the past 40 years, vehicle or the automotive industry concentrated on avoiding death and serious injury. This was called AIS-free plus. Some of you might know that. But as vehicles get safer and safer, also thanks to work like is done in Flex Crash, these injuries are not so deadly anymore. Death stagnating in Europe, slightly going down over the last 10 years, but still need improvement in these long-term consequences, because those are the ones that are critical for costs and well-being of our road users. So improving HPMs, ATTs, and test procedures related, and also improving road use specific countermeasures, protection solutions, post-crash treatment, and early detection on cognitive and mental health issues. As I said before, the ultimate goal is to reduce socioeconomic cost and consequences of injury, improving all our lives here. Going back a little bit to the original topics and questions, injuries, accident statistics are also here a very highly important aspect. Without good data, you cannot do a lot. And what we are doing here is really combine from road injury, trauma, and rehabilitation data and others, together with the medical data, and built here an initial assessment concept for our, in our case here, for road user groups. They are divided mostly by their needs and protection mechanisms. So we have pedestrians on one side, our vulnerable road user groups, active road users on motorcycles, bicycles, and especially new micromobility topics, e-scooters, e-bikes, these kind of things. that tend to appear, or not only tend, they really appear in the accident statistics at hospitals more and more on a highly critical level. So a lot to do for you, Peter, and colleagues to avoid these accidents or mitigate the consequences of them. And then we have our traditional vehicle occupants that are mostly the ones we want to protect with FlexCrash solutions and topics here. And the ones that usually tend to go under the radar is bus and shuttle occupants, especially inner city road users there. A lot of people fall in these buses and shuttles or trams, contact their guardrails and or their handrails, and more than you think appears in accident statistics. On the medical side, I will go over this very quickly here. We are basing our methods on a patient follow-up study on 4 different sites, to 4 different and 3 different regions of Europe. So getting a good spread on typical accidents from Central, South, and Southeastern Europe. It's a very interesting and rewarding work we do here. And on the engineering side, this is probably the part that interests you a little bit more. So a little bit more detail here. We are developing tools and methods for upgrading our HPMs, physical testing devices, and this goes especially in head, neck, and face brain injury, child protection, tibia fractures, very critical for if they break in an unsuitable way, hard to fix and related to long-term consequences. Calcaneus fractures, this is the heel of your foot, especially critical for scooters and pedestrians, and colliding with vehicles, and the traditional head and also face that tends to lead to critical long-term consequences, especially also on the psychological part. So if you are injured on your head and face, you tend to be unhappy. Pedestrian impact analysis, just very quick, and an upper arm case as a study for countermeasures are done here from our colleagues at CESAR and Lab, as well as CITOUT. And yeah, with currently promising results. Go into more detail on the slides then if you want, and especially come back to us if you have any specific questions. The part where I start to plug a little bit and promote a little bit road safety in general, we have joined and are currently co-moderating our road safety cluster with a lot of projects dealing specifically with occupant road safety and also infrastructure. So what we are really combining here, different aspects of road safety, promoting this. Please look at our road safety paper, especially on the relevant data. You can access this via this link here. And please also check the LinkedIn page that gets updated regularly. And a lot of these projects are currently in the final stage or preparing events. So please visit this topic here. On a Protect Us related impact, currently we are providing or having standardization efforts for data collection, data assessment, especially linking those 2 sources here. But there is still a lot of links missing, and neither hospital nor official road injury data currently collect this sort of data. So this is definitely an ongoing and long-lasting topic here. We have our ongoing multi-center harmonized data collection scheme that we're going to propose to be also used in our sister projects long-running studies here. Currently developing our road user countermeasures and effectiveness tools, and also to try to standardize there a little bit. And on the long run, the project goals is about socioeconomic cost reduction and including mental health and physical impairment, cognitive impairment here. So time is running a little bit. As you all understand, road safety for all road users is part of sustainable road transport. We definitely need a little bit more working together, more push that EU does not only have its Vision Zero, but also puts the money there. This is lacking lately a little bit. There are ongoing projects, but much more could and should be done in this context, especially if you want to avoid these socioeconomic costs a little bit more and more serious. So I'm currently trying to collect interest for Horizon Call 2026 on road safety and resilience of rural road areas. Not so much a crash and occupant topic, but an overall topic that brings everything together, a lot of infrastructure, vehicle-based systems, and these kind of things. So if you're interested in this, please contact us. It's to be submitted in October. And in addition to that, in September, we are going to have in Eurecat, it's a biomechanic conference on injuries with long-term consequences. There's a workshop there, pre-conference workshop, so please visit that there as well. It will be in Munich. And apart from that, hoping and pushing this topic, I count on your interest as well. Miriam, colleagues, I'm in discussion with Fanny continuously, so should work, and hope for more stuff here. Yeah, that was about Protect Us. You can reach me in this email, and yeah, looking forward to any kind of questions and input now or later. Thanks a lot.
So thank you very much, Werner, for the insights of OSCAR and Protect Us project. So I hope you get some insights of different ongoing research projects, starting from scenario creation, scenario-based virtual assessment, up to the end in injury risk criteria assessment from pedestrian and occupant safety. And now we are facing the Q&A session. My colleagues have to help me because I cannot see the chat on my screen. Are there any questions on the chat that we have to answer, or any direct questions from any participant that we can answer right now? If not, we can also provide the different presentations we have shown today, and if there are rising questions afterwards, then we can answer that also via different channels, email, LinkedIn, whatever. So once more the question, any questions from the participants?
I don't see any. Make some chat.
So nothing in the chat, no direct questions up to now. So I have to thank also Miriam and Sergi for setting up this possibility on the webinar for virtual testing methods on future relevant impact scenarios. That we can showcase a little bit the ongoing work, what we are doing at Virtual Vehicle, and I hope that was quite interesting for all the participants. And yeah, perhaps Sergi, a few words from your side at the end.
Yeah, thank you, Christian, and all your colleagues for the nice presentations. I hope that the attendants have just good notes from these different presentations, and new ideas will come for sure. Yeah, thank you all for attending this webinar. Yeah, I hope you enjoyed the different presentations and you have a new overview about the crash situation and the crash scenarios that we have nowadays.
So thank you very much for attending our webinar today. Perhaps a short outlook for the Grand Challenge CA conference in May. There will also be a presentation from FlexCrash, some results from the ongoing project, and perhaps I can see some of you there. Otherwise, well, thank you very much all for attending our webinar once more, and wish you a nice day, and see you soon.
Bye-bye, thanks.
Yeah,
Bye-bye.
thank you all. Bye.